So one kind of kinematics question that you often see is where two objects are moving with different velocities. Maybe one is chasing the other one, or they're both going in opposite directions and are going to meet at some point. Maybe two cars are coming in for a head-on collision. And you're often asked, how long is it going to take for the two to meet, and at what position do they meet? So this is an example of that kind of question. There are two ways to answer these types of questions. One way that can get you a pretty good estimate of what the answer should be is graphically. So you should be able to look at a distance versus time graph of two moving objects and be able to tell where they meet and how long it took them to meet. The other way is algebraically, so you should be able to solve them without a graph as well. So I'm going to show you how to do both of those. So I'm going to go ahead and set up my graph here. Now, I don't have graph paper, so I try to do my best and make everything as even as possible. That's one of the problems with doing this graphically, is you may end up with slightly off lines or slightly off slopes, so you may not get a perfect answer, but you can get a pretty good estimation. This is a distance versus time graph, so time in seconds is on my x and displacement is on my y, and I went ahead and put my displacement in meters. So my first cart is going to start at a position of 2 meters and has a velocity of 50 centimeters per second. Since I'm in meters, I'm going to have to change that to 0.5 meters per second. I'm starting at 2 meters, so at 0 seconds, I've gone 2 meters. At 1 second, I've gone 2.5 meters. At 2 seconds, so I'm going 50 centimeters or half a meter more per second. And so at 4 seconds, I should have gone 4 meters. And at 6 seconds, I should be at 5 meters. I'm getting a meter every 2 seconds. Okay, so I'm going to go ahead and draw my line for that. And I went ahead and extended it out because my car keeps going. So this is cart number 1. Okay, cart number 2 is going to start a little bit further ahead at 2.5 meters, but it's only going 20 centimeters per second. So it's going considerably slower. So it should have a shallower slope. So we're starting at 2.5, but it's going to take us 5 seconds just to make 1 meter. So at 5 seconds, I should be at a meter traveled. It's about right there. Okay, and then another 5 seconds gets me another meter. So then I should be at 4.5 at 10 seconds. I think that's about there. And let me go ahead and draw my line. Okay, so I have my two lines drawn to represent both of my carts. Now we just have to interpret it. So the first question says, how long does it take for them to catch up? Well, the place where they meet, or what represents their meeting point, is right here where the two lines cross. This is their meetup. Okay, so here we find that that is at a time of 2 seconds. So it takes 2 seconds for the first car to catch the second car because it's going considerably faster. And at what position do they meet? Well, position is over here on the X. So position looks to be right at about 3 meters. So graphically, that's the answer. Now we're going to go ahead and do it algebraically and see how close we got from our graph. So this is the same question. If we look at here, we can write an equation for each of these lines. So an equation is in the form of y is equal to mx plus b. The m is the slope, and slope on a displacement time graph is the speed or the velocity. The y is our displacement, so x is equal to the slope of the line, which is our speed, and we're going to go ahead and put it in meters, so 0.5. X is the time, t, plus b is the y-intercept, and so it crossed at 2 meters. So this is the equation for cart 1. For cart 2, x is equal to the slope for cart 2 was 20 centimeters per second, or 0.2 meters per second, times time, plus it had a y-intercept of 2.5 meters. So that is the equation for that line. Now, I didn't actually have to draw those lines and graph that to get those equations. I got all that information directly from the problem, if you know how to do it. So y is equal to mx plus b, to write an equation for the line, if you know the velocity or you know the slope and you know the intercept, then you can go ahead and write that equation. You don't always have it, but in this we have the information. So even without graphing that, I could write those two equations for those two lines. So here are the two equations for my lines. Now, if you think about what this means, at what position do they meet? Well, the place where they met was the place that their y values, or these displacements, are the same. So this needs to be equal to this. So we just set this up as an equality. So since this is equal to that and this is equal to that and x is equal to this x, if we want our displacements to be the same, then I can just set these two equations equal to each other. 0.5t plus 2 is equal to 0.2t plus 2.5. And now these two line equations are equal to each other, and now I just have to solve for t. I only have one variable, and so I can solve this now. Just use your algebra. So we're solving for t, so I need to bring my like values over. So this is being added, so I'm going to subtract. I get 0.3t is equal to, this goes over here, is equal to 0.5. T is equal to 0.5 over 0.3. T is equal to 1.67 seconds, which is close to what we found over here. We got 2 seconds. This is the better answer because this is more accurate. Remember how I said it may be a little bit off, but we're pretty close to what we had over here. Now, if I want to know the position, I could rearrange both of these so that they're both arranged for time, and t equals this and t equals that, and then set them both equal to each other and solve for x. But since I have to know both, the easier thing is just to take this number for time and plug it back into one of the equations. You can pick either one, it doesn't matter. So x is equal to 0.5t plus 2. I just took this equation. I'm going to plug this number in for time. So x is equal to 0.5, 1.67 plus 2. X is equal to 2.835 meters. So this is the position at which they meet, and this is the time at which they meet. And up here we got 3 meters, 2.85, pretty close. This is the right answer down here. Now, just to make sure, just to show you that you get the same answer for both, if I were to plug it into the other equation, x is equal to 0.2t plus 2.5. X is equal to 0.2. I'm going to plug in my t value, 1.67 plus 2.5. And I solve for that, and I bet I'm going to get 2.8 something. 2.834 meters. So, same answer. The only difference there is rounding. But they both round to 2.8. So it's going to be a time of 1.67 seconds, and the position that they meet at is 2.8 meters from the origin. Okay, so that's how you solve a question like that. If they were coming at each other, you would just have to make sure that you one of them's velocity is going to be positive and the other one's going to be negative. Just be careful with that. And if one starts at a position of that's before, they could have a negative position before the origin. Again, you just have to watch your signs, make sure you plug your signs in correctly to your equations, but they all solve the same way.